Oh, these are my, oh yes, my quiz, the quiz of review. Do I have all the quizzes of review? No. Thank you.
진짜 이번에 파이널 보고 약간 이 맞아 읽었으면 진짜 불안해.
So I will look at the solution to the quiz of review in the help session. Oh, can you hit record? Or, oh, you did? Okay, great. Let's see here. So I don't actually have these printed out for you, but what I'm going to do is I will attach one of these to each final that I give, and then if you feel like you want to fill it out and turn it in, you can do that to the secretary individually, and then she'll collect them and I'll take them from her later, okay? And that won't look at them until, of course, after I'm done grading finals and stuff, right? Like I usually do. So it is important, though, for you to fill out the electronic one. And it's also important for me to take a minute or two to explain how to fill it out. So here we have the usual boilerplate questions. I don't really have much to say about that. I have a few modifying. Like number 9, it says instructor provided helpful feedback on assignments. I have added in italics, for example, provided solutions to homework quizzes or tests. Question number 11 is more important. I always include this modification. You know, I would recommend this course to a friend. It's important to think, you know, you should assume your friends have similar life goals. This question is not asking you if someone from a non-technical major should take this course, right? I mean, to be clear, this friend, this hypothetical friend, is someone else in the math major, right? Not applicable? Like you don't have any friends? Whenever I read not applicable to that question, like I see not applicable on that as a response, that makes me go, aw, aw.
All of my friends are quite really misreading.
But here's the thing you got to understand. Because administrators view these in terms of one composite number, to mark not applicable is to more than strongly disagree. You said it was stupid. I wouldn't say such a thing. I'll let you say it. Thank you. But it does seem stupid, yes. Not that I'd say that. But. Let me go on here. I do actually have material to cover today. The amount of time, you guys always rip me apart on this one. The amount of time was required in this course. Blah, 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 was reasonable. And then I say, this is not asking if the time was comparable to other courses you're currently taking. That which is worth doing is often difficult. What you should ask yourself here is, could I have done less and still have understood the content of the course? Did I give you busy work, or did I give you work which was needed to build the skill this course intends to impart to you? So, yes. Not applicable. Hey! You could at least just disagree. Just disagree. Don't be not applicable. If you disagree is the new not applicable. I'm particularly proud. I've been working on 17 for a while. I had a better statement of this in differential equations yesterday because I asked them the question, who's the author of truth? You know who the author of truth is, right? Is math part of truth? I hope you can agree. And then I would add the following question. Did we do math in this course? The answer is yes. So we have studied God's truth in this course. So to say that there was not biblical integration in this course is to deny that math is part of God's truth. Do you want to be that person? The answer is clearly no. Not applicable is more than strongly disagree. Ah, see, I was supposed to have given you this. I was supposed to give you guys this speech before Thanksgiving as to properly skew my statistics.
See, wait, but the last question there says, do you really want to say that? I don't want to say that. Why should I disagree that I want to say that?
Like I said, I'm working on it. All right. Anyway, and then I have some short answer questions, which I'll let you look at after you take the final, and so. All right. So I hope you're enjoying the ice cream. And I think we can all agree that, when you look at, I just want to say that, this looks amazing, right? This looks like it would be phenomenal, doesn't it? What is your opinion of this? You liked it? It's not bad?
It doesn't live up.
But it's not this, right?
Yes.
This is something else.
I agree.
Right.
Not as epic.
Yeah, it was not what I was hoping. Now, in contrast, the Reese's Pieces ice cream there, that is exactly what you expect it is. So that's good stuff. All right. Well, I'm still supposed to tell you some math in here. And I would again caution you, I'm not here Monday, so, don't come to class. I will not be here Monday. So let's see here. So I sent you guys an announcement with my office hours next week. So I have non-standard office hours next week, some Tuesday, some Wednesday, some Thursday. If those don't work for you, let me know. I can probably work something else out, but you got to let me know ahead of time. So I wanted to just give you a little talk, and apparently it's going to be a very little talk, on Li algebras. Now this is posted in course content, right? So you don't have to really write anything down. You can just read along with me. And so this is taken from Erdmann and Wilden's book, Introduction to Li algebras, which is a delightful little undergraduate text. It's very close to the set of course notes which my Li algebra course was based on at NCSU from Dr. Misra, who happened to be my brother's advisor. The math my brother studied is kind of infinite dimensional Li algebras of some sort, roughly speaking. It's not that exactly, but it's kind of that. And this is the definition of a Li algebra. A Li algebra is a vector space with a multiplication which is not quite associative. So this Li bracket, it's bilinear, all right? It's a bilinear map. It's linear in each slot. And it satisfies this condition. And it satisfies axiom 2 here, which is kind of more complicated looking. And what this is really saying is that, this is describing how it's not associative, yes, but it's also satisfies this. So this is sort of it's not quite associative, but it satisfies this Jacobi identity. And so Li algebras are something we find in applications. It's not just, oh, let's make up some abstract algebraic system and study its properties. I mean, that's the approach and the posture of the course I took and also of this book. But the fact of the matter is Li algebras pop up in all kinds of applications. You can go to graduate school, not be a Li theorist. If you're just studying pure math of some sort or another, you will find yourself needing to know Li theory, even if you're not a Li theorist. A lot of different parts of math use Li algebras. Anyway, the first thing I can prove is that axiom 1 actually is equivalent to saying that the bracket is skew symmetric or it's alternating. So if you look at x plus x being 0, x plus y times x plus y like that, the Li bracket of that, well then by bilinearity you get all this, but that's 0, so it shows you that xy is equal to minus yx, as you can see here. So axiom 1 can also be replaced with alternating. Now I think that's only true if the characteristic's not 2, but anyway. So some examples. In Calculus 3, for those of you who've had it, everybody have it? Everybody's had it, okay. The cross product actually is an example. If you take the R3 paired with the cross product, that's a Li algebra because the cross product satisfies the Jacobi identity. A cross B cross C, if you cyclically permute that with ABC, keeping the parentheses in mind, you get 0. But in fact, the cross product is also a great example of something which is not associative, right? So go-to examples of operations which are not associative would be, for me, the cross product or subtraction. Right? Subtraction is not associative. Now, any vector space, if you just give it the trivial bracket, that gives what's called an abelian Lie algebra. If you take any vector space of finite dimension and you look at linear transformations over that, you can make that into a Lie algebra where you use the composition of maps, and this is the Lie bracket is T composed with S minus S composed with T. This is the bracket. Oftentimes called the commutator bracket. The reason that's called the commutator bracket is kind of simple. If it's 0, that means the transformations or the matrices commute, right? Likewise, n by n matrices is a Lie algebra. With respect to the commutator bracket, you can show that that satisfies the Jacobi identity. That makes a great linear algebra exercise. Perhaps you experienced it. I don't remember. About every other year I assign it. Now, you can calculate the Lie bracket of the matrix units, and it works out to that. That's actually useful for certain homework questions that I might have assigned. All right? SLN, the special. So be careful in the homework. Little s is the Lie algebra. Big S is the Lie group. Little SLN it's the set of traceless matrices. Big SLN is the set of determinant 1 matrices, invertible matrices. So this is the Lie algebra of the big SLN Lie group. And we talked about the connection between those in the earlier part of the course, right? So I'm kind of not touching much on that at the moment, that geometric matrix Lie group part of it, but that's still there. We're just focusing today on just the abstract algebraic aspect of Lie algebras. You can also talk about upper triangular matrices, which we denote by BNF, or strictly upper triangular matrices like NNF. So the N is for nilpotent, really. Because any matrix you take in here, if you start raising it to a power, think about if you have a matrix which is strictly upper triangular, if you start raising it to a power, what happens? The things above the diagonal, like the superdiagonal, or the superdiagonal, or the superdiagonal, whatever you call those things, they kind of like shift up and drift towards the corner as you take powers, and eventually they just go right off the screen, and you have the 0 matrix, right? You guys maybe don't know what I'm talking about. Let me. Oh man. Oh, back there, huh? So, for example, this thing would be, this would be an element of n3 r, right? And n squared is what? And n cubed is what? So the nilpotent matrices, the strictly upper triangular matrices, I should say, they will, after a short time, power to 0, right? Okay, so those are all examples of Lie algebras. In fact, some of them are examples of sub-Lie algebras. What's a sub-Lie algebra? It is a subspace of the given Lie algebra, which is again a Lie algebra with respect to the inherited bracket. So, for example, SLN, the upper triangular, strictly upper triangular, these are all subalgebras of just the n by n matrix Lie algebra. All right? This one, I think, this is one of your homework problems, right? To show that the nilpotent matrices are a subalgebra of SLNF. So what would it take to show something's a subalgebra? What would the test be? It needs to be a subspace, which is also a Lie algebra on its own right, right? So if you know that the commutator bracket satisfies the Jacobi identity, and so you know that the commutator bracket satisfies axioms 1 and 2, right? That's still true if you look at a subset of matrices, right? So all you have to do is do what? You have to show that if you take the commutator bracket of two nilpotent matrices, you get a what? You need to show that the Lie bracket is closed on the the upper, strictly upper triangular matrices. In other words, that the commutator bracket of two nilpotent matrices is again a nilpotent matrix. That's actually pretty easy. If you think about A and B being strictly upper triangular, and you look at the product of A and B, what can you say about it? If you study it, you'll see that it's also strictly upper triangular. And likewise for BA. And if you take the difference of two things which are strictly upper triangular, you get what? Something is strictly upper triangular. I mean, that's essentially how to show that the n sub n ninf is a subalgebra snf. Yeah. Sorry, I'm an idiot. Let me go on. What's an ideal? An ideal of a Lie algebra is a subspace such that it satisfies Uber closure, right? So x bracket y is in I for all x in L and all y in the ideal. So this is, more or less the same notion we had of ideal in a group, right? Yeah. Maybe a ring. Why don't I need to check that yx is also in I? Remember, we proved the axiom 2 is equivalent to saying xy is equal to minus yx, right? So if we know I is a subspace, there's no need to check the other bracket. If xy is in there, yx is also in there for free by the thing I proved on the first page. Examples of ideals. SLN is an ideal of GLN. The nilpotent matrices are an ideal of the upper triangular matrices. 0 and a Lie algebra are ideals of any Lie algebra. The center of a Lie algebra, Z, that would be the set of all elements of the Lie algebra which commute with everything else in this sense. That is also an ideal. If the center of the Lie algebra is the whole Lie algebra, that means that L is an abelian Lie algebra. Possible homework problem. Find the center of SL2F. Note the dependence on the characteristic of F. What's the characteristic of the field? The number of times we have to add 1 to itself to get back to 0, right? If it's possible. If it's not possible, we say it's characteristic 0, like rational numbers, real numbers, complex numbers, right? Did I assign that?
No.
Oh, man. Lost my chance. It's okay. You can do it in the Lie algebra course we offer here. Okay, just mess with you. It's conceivable that this is offered as an undergraduate course, but there's not many schools with an undergraduate course in Lie algebras. That's true. But there are a lot of instructors who, like me, think it's important to mention Lie algebras to undergraduates because it's playing such a large role in the discussion in graduate school. All right. So anyway, you can talk about Lie algebra homomorphisms. That's going to be. I also like this. I like this discussion because it gives us a chance to see all of the familiar faces again in yet a new context, right? Subspace. I mean, the sub idea, the sub object, the ideal object, the homomorphism idea, right? Soon the first isomorphism theorem again, but in our current context. So here, a mapping from a Lie algebra L1 to a Lie algebra L2 is a homomorphism of Lie algebras if it preserves the bracket. And it also, notice I buried it up here in the preamble, it has to be a linear transformation. So it's a linear transformation that preserves the bracket. That's a Lie algebra homomorphism. If it's in addition a bijection, then it's a Lie algebra isomorphism, and we say that L1 is isomorphic to L2. So obviously, an important question to ask is when are two Lie algebras isomorphic, right? And that question has been pretty well answered for a lot of cases by work of mathematicians over the past century, or a little bit more than that. Anyway, theorem, you can define the adjoint map which goes from L to GLL. In other words, it takes the Lie algebra element and it trades it for a linear transformation on the Lie algebra. And you define the adjoint map of x by this. Add x of y is equal to the bracket of xy. So for each x, I'm mapping y to xy. And that's a linear map because we assume bilinearity of the bracket. It's also linear in x because, yeah. So in fact, this adjoint map is a Lie algebra homomorphism. And the kernel of the adjoint map is in fact the center. It's pretty easy to see that the kernel of this map is the center, right? What would the kernel of the adjoint map mean? It'd mean that add x mapping to the 0 map. So if add x is the 0 map, what's that mean? It means that add x of y is equal to 0 for all y. That is to say that x is in the center of the Lie algebra. So the kernel of the adjoint map is in fact the center of the Lie algebra. Definition, well, here's the definition is that this theorem gives us something that we can define. And the adjoint map is the adjoint homomorphism as it's known. So if we have a mapping from L1 to L2, a Lie homomorphism, then the kernel of phi is an ideal, and the image of L1 is a subalgebra of L2. So this feels like familiar ground. This is part of the first isomorphism theorem, right? You can also talk about derivations. A derivation is a formal abstraction of the notion of a derivative. And that's one of the reasons that Lie algebras are so ubiquitous in advanced math, is because when you look at differentiation from an algebraic perspective, you find a Lie structure. And how many parts of math involve differentiation? Like a lot, right? A lot. So a derivation, though, is just a linear map. And you can talk about a derivation more generally than just a Lie algebra as well, because here I talk about a derivation with respect to just an abstract multiplication, like an associative algebra actually here. And so a derivation of an associative algebra would be like this. But in the case that we're talking about a Lie algebra, the derivation rule looks like this. So d is a derivation if d of the bracket is equal to x bracket dy plus dx bracket y. So this is the Lie algebra version of the product rule. The derivation satisfies the product rule. So first and foremost, of course, if you take the algebra of smooth functions, then the mapping f goes to df dx is a derivation. Well, that seems good, right? Because it satisfies the product rule. Yeah. The Leibniz rule is literally the Leibniz rule here. But anyway, you can also prove that the adjoint is a derivation, right? So what would it take to prove that the adjoint is a derivation? You need to show that if you replace d up here with add, it's true. So I would need to show that add of xy is the bracket of x with add y plus add x with y, I believe. And I think for that, well, anyway, I don't want to say more. But that's not that hard of a problem. You just have to sort through it. We can also talk about structure constants. I don't really have much to say about that, except to say that if you define the bracket on a basis, if you give constants which tell you how to take the bracket of a basis, then you extend that bilinearly, that uniquely defines the Lie algebra. Now, that's subject to the terms and conditions that you've given a set of constants which actually satisfy axioms 1 and 2, right? You could give me a set of constants which somehow encode a departure from the Jacobi identity, and if you did that, I'd be out of luck, right? So they have to be consistent with the axioms, but if they are, then you can extend bilinearly and get a whole Lie algebra. So there's, if you study the study of Lie algebras, especially as it gets older, it's much more about the structure constants. Nowadays, it's more about linear transformations and studying properties of abstract maps. But it used to be about studying structure constants. So for example, the structure constants for the cross product algebra, one of my favorite formulas from Calculus 3 is that the formula for the cross product of V and W is epsilon ijk vij ek summed over ijk from 1 to 3. And if you focus your attention just on the basis elements, like if you take ei cross ej, you get epsilon ijk ek in the sense that like e1 cross e2 is equal to epsilon 1, 2, 3, e3, right? And so this is the structure constants actually for the Lie algebra of R3 paired with the cross product are the Levi-Civita symbol, which we can also use to build the cross product. But anyway, I don't think I've actually asked you a homework question about that, have I? Not really. Should have. Oh, well, I lost my chance. We can talk about building new ideals from old. So like the sum of two ideals is an ideal. The bracket of two ideals. Now this will catch you off guard. If you're not paying attention, this will get you into trouble. If you think that the bracket of two ideals is just straight brackets of two things, it's not quite right. You actually have to take the span of brackets from the respective spaces to get the ideal. This set without the span can be different and also not an ideal. But anyway, I don't have an example for that. An example for that, of course, is given in Erdmann and Wilden, if you're interested. But anyway, one of the interesting things is that if we have the ideal SL2C, which is the special Lie algebra of 2 by 2 complex matrices, so traceless 2 by 2 matrices over the complex numbers, then you can actually prove that the bracket of two of those things is again the same form. So that's an interesting result. And of course, what are ideals useful for? They're useful for setting up the quotient Lie algebra, right? So the quotient Lie algebra is the set of cosets, all right? So we define the quotient vector space as we might have done in linear algebra, some of us. And then we take that quotient vector space and we give it a bracket. And the way we bracket is to bracket the representatives of the quotient of the cosets, just like you'd expect. And the ideal condition is exactly what you need to make this bracket well defined, and also to satisfy the Jacobi identity, as you would hope. Here is a quick check on the bracket being well defined. So we'd like to see that x prime y prime is equal to xy if we're given that x and x prime and y prime are two different representatives for the same coset, right? So in other words, I want x plus I equal to x prime plus I, and I want y plus I equal to y prime plus I, right? So x prime y prime would be equal to that. I'm just adding 0, right? And then I use the bilinearity to expand like so. And I've got xy, and I've got these three things. Y prime minus y is in I, because I is an ideal. X prime minus x is in I because of this condition and that condition, actually, right? This condition gives me that that's in I. Gives me that x minus x prime is in I. And this equal to that gives me that y prime minus y is in I. But since I is an ideal, x with anything in I is an I again. And since I is an ideal, y with anything in I is an I again. And over here, you've got two things in I, which bracketed together give you something in I again. So you've got a sum of things in I again. So I. It's all in I. All right, so great. So this plus this is equal to this plus something in I. In other words, the difference of that bracket and that bracket is something in I, which is to say that it doesn't matter which representative we use, we get the same Lie bracket. Is this argument new? Not particularly. I mean, the details are a little bit different. We're using bilinearity of the Lie bracket to prove this, right? How did it go before for the factor group? To prove that the factor group is well defined using the normality of the subgroup. The argument, the big picture of the argument was much the same, but there we were dealing with group multiplication, right? And the corresponding factor group multiplication, as opposed to now the Lie bracket multiplication. But intuitively, it's really the same argument. I mean, now, by the way, you can talk about the natural coset map, pi of x maps to x plus I gives the Lie homomorphism as well. All right. So there are isomorphism theorems, one of which we've covered this semester. The first isomorphism theorem says that L1 mod the kernel of phi is isomorphic to the image. Still true for Lie algebras. Yay! There are also a second and third isomorphism theorem, which I will talk to you about more in Math 422. Although they also make, admittedly, they do make nice questions for the final, but I should probably not do that. I mean, the proof of the second and third isomorphism theorem, it's just stuff that you've learned this semester, put into practice. I mean, the proof of the first and the second and third isomorphism theorem is, you know what it's built off of? The first isomorphism theorem, yeah. I'll leave it at that. And the trace gives us an example of a Lie algebra homomorphism. You can prove this, all right? So the trace goes from the general linear algebra, GLNF, to F. Well, this is just n by n matrices with commutator bracket. And it's easy enough to see that the kernel of the trace map is what? You're sending matrices to 0. In other words, what matrices go to 0? The matrices with 0 trace. So the kernel of the trace map is exactly, by definition, little slnf. So this shows you that GLN mod SLN is equal to the image of this, but it's easy to prove that the trace map is surjective. Now that does feel more like one of your homework problems, doesn't it? I feel like I asked you to show that in the homework, didn't I? So what's left? What have I not done in the notes to actually prove that this is a Lie algebra homomorphism? What do you need to do? You need to convince me that you believe that it's a linear map. Is this a known property of trace? Is the trace of A plus B the trace of A plus the trace of B? Yeah, we did prove that. What are properties of trace that we've proved in linear algebra? We know that the trace of the sum is the sum of the traces. We also know that the trace of AB is equal to the trace of BA. Right? Like the trace, you can commute inside the trace. So I think if you know those two things, and you know that the trace is a linear operator, you'll be able to prove that the trace is a Lie algebra homomorphism, which would mean what? The trace of the bracket is the what? The bracket of the traces, right? The trace preserves the Lie bracket, which is kind of silly here because over here the Lie bracket is just multiplication of numbers, which is, I don't know. There's almost nothing to check here really, but do go through it. Now, chapter 3 in Erdmann and Willman actually classifies low-dimensional Lie algebras. I'm a little bit short on time, so I'm going to skip past this today. But long story short, there are just a couple. Here they are. There actually are, well, I guess there's an infinite family in 3 dimensions, but in 2 dimensions, there's really just 2 up to isomorphism. Next up, you start talking about solvable Lie algebras. The question about a solvable Lie algebra is, what does it take to make the quotient by the ideal abelian? So this lemma says, if I is an ideal of L, then L mod I is abelian if and only if I contains the derived subalgebra. So the derived subalgebra, L prime, is the bracket of L with L. All right. And so this is the lemma that makes everything happen. Let me just read it again. I an ideal of L, then L mod I is abelian if I contains the derived subalgebra. And the proof is relatively simple. It's right here, but again, since we had ice cream today, you'll forgive me. Now, L, the derived subalgebra, it's the smallest ideal of L for which the quotient algebra is abelian. All right. So, because if you have an ideal whose quotient is abelian, then L prime contains it, right? So that means that this is the smallest one, giving an abelian quotient. And so this leads us to define the Derive series. The Derive series of a Lie algebra is given by L1 bracket, which is L prime. Then the second derivative, so to speak, is L prime with L prime. Generally, the kth derivative of L, so to speak, is the bracket of the k minus 1th with the k minus 1th. And you can notice that that satisfies the descending condition. It's right, descending series like this. And so the Lie algebra L is said to be solvable if for some m greater than or equal to 1, we have that the mth derivative and beyond of the algebra is 0. So you may or may not remember this at this point, but I showed you a couple slides ago that SL2C bracket SL2C is equal to SL2C. So that means that the derived series of the special Lie algebra SL2C is not solvable because it doesn't ever do this. Yep.
Sorry, I just have a question about the derived series.
Uh-huh.
L2 is equal to bracket. Is that L prime or L1 L1?
It's L prime, L prime.
Okay, so then when you say that LK is equal to the bracket of LK minus 1, is that K minus 1 prime? Or is that
This
like
is,
K minus 1
well,
prime?
L prime is one bracket. It's not at odds. I mean, this is the same
Okay, gotcha.
L2 with one L.
Okay, gotcha.
Yeah, yeah. Now, there is something later that doesn't have the brackets, but first. Now, what are examples of solvable algebras? The Heisenberg algebra is solvable, which if you can tell me what the Heisenberg algebra is for my notes, that would be very impressive because I've never anywhere defined it for you in these notes. Hey, sorry. The upper triangular algebra is solvable, but there's this thing called Google. You could look at the Google. It'd find it for you. It's not that hard, the Heisenberg algebra, but again, you can study in our Lie algebra course here. And so you have an upper triangular algebra solvable. Any two-dimensional Lie algebra actually is solvable. And again, as I was just saying, SL2C is not solvable because, in fact, the derived algebra is L again for m equals to 1, and then by process of extension for all m. Yeah. Now, there's a claim that I could make here, which is that if we have a surjective Lie algebra homomorphism, then the image of the kth derivative of the algebra is the kth derivative of the range, right, of the image. And with that claim above in hand, it's evident that if you have a solvable L, then every subalgebra and every homomorphic image of L is solvable. It's also clear that if L has an ideal I and both L and L mod I are solvable, then L is solvable. So like if you can divide and conquer. If you have an ideal which is solvable and the quotient is solvable, it follows that the whole thing is solvable. We've seen some theorems like this, right? You experienced this kind of theorem on a test. I feel like test 2 might have had the, was it test 3? Which was the, well, let's see. We'll know when we're not quite there yet. We'll know when we see it. But if I and j are both solvable, then I plus j is solvable. So you can build solvable begets solvable in these sense. Claim if L is less, dimension of L is less than infinity, then there exists a unique solvable ideal of L which contains every solvable ideal of L. So this unique solvable ideal which contains all other solvable ideals is called the radical. All right, so rad L. And a non-zero finite dimensional Lie algebra L is said to be semi-simple if it has no non-zero solvable ideals and the radical of L is, in other words, the radical of L is 0. So lemma 4.7 in Erdmann and Wilden says that L mod the radical of L is semi-simple. I wonder if you rewrite this claim as being that the radical of L mod the radical of L being 0, does that perhaps give you any sense of deja vu? Uh-oh. My joke is not working. This is like the nilpotent of L mod the nilpotent being just 0 again, right? Yeah. It's that thing. Sorry, it's too soon. Too soon. You can also talk about nilpotent Lie algebras. A nilpotent Lie algebra is defined down here, but this leads us to yet another thing, the so-called lower central series. So it starts out the same, like L1 without the parentheses is the derived algebra, but L2, for example, would be L with L1. So this is kind of what you're asking about, Liam. See, I mean, this is more like what you're asking. The lower central series, it's L with the L1, L2, L3, and so forth. So LK with LK minus 1, but just the second one, not both of them. It's a different series than the one we were looking at, the Derive series. And proposition, LK is an ideal of L, and the quotient of LK and LK plus 1 is contained in the center of the quotient of L with LK plus 1. That's why it's called a central series. Now, so a Lie algebra is said to be nilpotent if eventually the central series is 0 past some point. And again, the strictly upper triangular matrices are nilpotent. Any nilpotent algebra is solvable. That's kind of not that hard to see. And there exist solvable algebras which are not nilpotent. For example, this is a algebra which is solvable but not nilpotent. Yes, Liam?
Okay. So again, so hold on. It looks like I just thought by one note that if L is the definition for solvable and nilpotent looked exactly the same.
The solvable involved the parentheses. The nilpotent involves no parentheses, is the short answer to your question. Let me finish this here.
Okay.
So lemma 4.9 says that, let me just get to the big picture here. So the radical of L is solvable, and L mod radical of L is semi-simple. So if you can understand possible forms of solvable and possible forms of semi-simple Lie algebras, it gives you a hope of classifying. A Lie algebra is said to be simple if it has no ideals other than 0 and L is non-abelian. And from the work of Killing, Engel, Cartan, it turns out that with 5 possible exceptions, every finite dimensional simple Lie algebra over the complex numbers is isomorphic to one of the following classical Lie algebras: SLNC, SONC, SPNC. These are the Lie algebras. These are the Lie algebras of the, the special orthogonal and the symplectic matrix groups I showed you. And so these are infinite families. As n goes on, you get an infinite series of them. And then there are 5 exceptional simple Lie algebras: E6, E7, E8, F4, and G2. This G2 gives you that G2 holonomy, which has been extensively studied in string theory lately. And that's it. So anyway, I have another comment or two here about associative algebras, but that doesn't matter. Anyway, I hope I have told you enough to make the homework accessible. I will help you with that homework in the help session today if you have further questions. So, and also help yourself to more ice cream on the way out if you want. There's no class Monday. Yep. Yep.